Hello. Today we're going to be solving this problem. If A and B are two sets, prove that A is the union of a disjoint pair of sets, one of which is contained in B, and one of which is disjoint from B. To start, let's translate this question into mathematical notation. Okay, so I want to show that A is the disjoint union of two sets, or the union of a disjoint pair of sets. So let's call them E and F. And I want E to be contained in B. And I want the other set to be disjoint from B. Recall that a set is disjoint from another set if they have no elements in common, i.e. their intersection is empty. Okay. So with this in mind, let's translate the question in the following way. Let A and B be sets so that there exists sets E and F such that A is the disjoint union of E and F, and E is contained in B, F is disjoint from B. All right, wonderful. So, first of all, I should note this disjoint union notation. So recall the union notation is, if you look at my last video, I explained that definition, but an element belongs to a union if it belongs to one of the sets. So recall that X belongs to E union F if X belongs to E or X belongs to F. Okay? Now this disjoint union symbol simply means that the same definition, it's still the definition of a union, but I'm actually specifying information about these two sets, namely that they're disjoint. Okay, so this just means, this symbol means that E and F have no, or sorry, E and F, their intersection is empty, which means they have no elements in common. All right. So if you need a more in-depth refresher on this set notation, please watch my previous video. Now, moving forward, we see that we want to express A as the disjoint union of two sets. If we draw a picture, then perhaps, I draw A as this abstract ball here, and then B could be anything, okay? It doesn't have to intersect A, it could be any other set. And so the idea is that I want to look at the pieces of A that are contained in B, and then the pieces of A which are contained in outside of B. Okay? So this is the idea. Okay. So the idea is, in mathematical notation, is that A should be somehow the pieces of A that belong to B. So this is A intersect B, and then union with the pieces of A that don't belong to B. So this is union. This is the intersection of A with the complement of B, where B complement is defined to be the set of all X within our underlying space, such that X does not belong to B. Okay? All right. So this is our idea. Intuitively, it seems correct. We could draw a picture to represent what's happening here. How do we prove this more rigorously? So the proof is in the following way. Essentially, we're going to use the result of the previous exercise. And I am going to write A as A intersected with the whole space X. Okay? So let's say A and B are sets, and with A and B being subsets of a larger space X. This is implicitly assumed in the problem. If A and B are not both subsets of a space X, then we really have nothing to talk about here. Okay? So X is our total space. I have A as A intersect the total space. Okay? This is clear because an element is always, X is always in big X. So this equality follows from the fact that if X is in A, then certainly X is in A and X is in X. And if X is in this set, then clearly it's in the set A. Okay? Now, I'm going to write X as the union of two disjoint sets, namely B and its complement. Okay? And so you can check that if I look at the set B, if X is in B union B complement, this means that either X is in B or X is not in B. But this statement is tautologically true. It's true for all X in our underlying space X. So this is always true, which means that X is X can be any element of our space, and this statement will always hold. Therefore, I can rewrite the whole space as this union of B union B complement. Now notice also that B and its complement are by definition disjoint. Okay? So B intersect B complement is the empty set by definition if X is in B and X is in B, X is not in B, i.e. X belongs to B complement. This statement can never hold. Therefore, there's no element which satisfies this statement, so it's tautologically false, and therefore this set is the empty set. Okay? That means that B and B complement are disjoint sets. Another term is that this disjoint pair, their union is the total space X, and so we say that B and B complement form a partition of the space X, which is just fancy terminology for saying that they're disjoint sets whose union is the total space. Finally, we're going to apply the previous problem, which allows us to use this algebra of set intersections and unions to write this as A intersect B union A intersect B complement. And this is by problem 2. Okay? All right, and now we're almost done. So these are our sets E, and this is my set F. Okay? Now I just need to check that these two conditions hold. All right? So now we're going to note that A intersect B is a subset of B. Okay, why is this set a subset of B? Well, if X is in A and X is in B, i.e. if X belongs to A intersect B, then automatically, of course, X must be in B. Okay? So this is a clear set theoretic conclusion here. And then the last thing we have to check is that A intersect B complement. So A intersect B complement is disjoint from B. So intersect B is equal to empty. Okay? And this is since, okay, you can you can use the same logic as the previous argument and argue in the following way, that A intersect B complement intersect B is a subset of B complement intersect B, which we've already shown by definition is empty. And anything that's a subset of the empty set is, of course, empty. Okay? So notice that there's other ways we could have done this, but one little detail that I want to point out is that notice the associativity here, where in general, if I have parentheses, I need to take the order of operations into account when I'm doing the set algebra. However, if I have intersections, which are a composition of the intersection of sets, then actually this operation is associative. So it doesn't matter, if I first intersect A with B complement and then intersect with B, I could intersect this set in any order. I guess what I should say is that A, so I guess note is a general fact that A intersect B intersect C. This is just equal to A intersect B intersect C. So intersections of sets are associative in this way. And that's just because of the symmetry of the definition, right? If any element belongs to this set, well, then it must belong to all three. If X belongs to this intersection, then X must belong to A, B, and C. Okay, so that concludes our proof.